Hi, in this video, we want to take a look at conditional probability. All right, conditional probability is how we incorporate prior knowledge that we know to be true in the scope of likeliness of an event. Okay, so the big thing here, the big concept is I already know something is correct, and I want to mathematically incorporate that knowledge into the situation to give me a more precise view of what is going on, and that is conditional probability. So now let's go ahead and get into the math of it. All right, so what we're going to do is that, let's say I've got two events. Mathematically, we have event A and event B. Okay, so conditional probability of A given B, so this is important, A given B. So we're saying that I know what's going on with B is true and correct. And then I want to know how likely is the event A to occur. And we're going to write this as the probability of A given B. So when I say given, I'm saying that I know that the event B is 100% going to happen or did happen. And our formula for this is probability of A given B here is the probability of A and B happening divided by the probability of B. And this only makes sense if the probability of B is greater than 0. Otherwise, we can't do division. Okay, so for example, let's say that we have a box of 5 light bulbs, and there's one that is defective. Now, I'm going to just reach in, I'm going to grab some light bulbs, and I'm going to put them into the sockets. Now, let's say that I know that the first one was non-defective. What is the probability that the second is non-defective? All right, so given that the first one was non-defective, what's the probability that the second one is non-defective? So I went in, I grabbed light bulbs, I put the first one in, turned it on, hey, that works. What's the probability that the second one is non-defective? All right, now, this seems like a weird example, but this type of reasoning through is important for things like quality assurance of seeing if I have like what likelihood I have a defective piece coming down the line. Now, this is a very simple example, simple calculation, but this is like the spirit of other things that are more interesting that actually used in industry. Okay, so I'm going to say that N is non-defective, and the subscript indicates which light bulb we're talking about. So subscript 2 is talking about light bulb 2, and subscript 1 is talking about light bulb 1, the first one I grabbed. All right, so the probability that light bulb 2 is non-defective, given that the first one is non-defective. So here I'm saying I know the first one is non-defective. All right, well, the likelihood that we're going to be talking about is the probability that both of them are non-defective divided by the probability that the first is non-defective. Okay, well, how do we calculate this? Well, the probability of both of them being non-defective is the probability that I grabbed 2 out of the 4 good light bulbs divided by all the possible ways I could grab 2 out of 5 possible light bulbs. So here, this 4 choose 2 up top is me reaching in and grabbing 2 of the 4 good light bulbs. Down here, this is all the different ways I can grab 2 of the light bulbs from the box of 5. And so this ratio gives me the probability of grabbing 2 good light bulbs. Now down here, this is the probability of this part here. Let me see if my mouse is not agreeing with me. There we go. This is the probability that the first light bulb is good. So the number of ways I can grab 1 good light bulb divided by the number of ways that I can grab 1 light bulb, good or bad. Okay? So now let's go ahead and do some calculations. So when I compute these numbers, this is 6 over 10, and this one is 4 over 5. So I see I have a fraction on top of a fraction. Dividing a fraction is the same as multiplying by the reciprocal. Here I just do a little bit, I simplify the 6 over 10. Then I multiply by the reciprocal and simplify, and that gives me the conditional probability. Okay. Now, conditional probabilities satisfy the axioms of probability overall. So first, I know that A and B, A intersect B has to be smaller than B as a set because it's an intersection. I know that this is true from basic set theory. Therefore, it has to work out that the probability of A intersect B has to be less than or equal to the probability of B. The probability of both occurring has to be less than or equal to the probability of B by itself. So A and B is more restrictive. Okay, well, both of these are probabilities. The probability of A and B and the probability of B, they're probabilities. So they're both between 0 and 1. Now, if you do a little bit of college algebra and some reciprocal work, we're going to see that this ratio has to be between 0 and 1 whenever the probability of B is greater than 0. And so it works out that the conditional probability is between 0 and 1. Now, for the second axiom, the entire sample space has to have probability 1. All right, well, what we're going to do, we're going to take our formula. I'm going to replace A with the entire sample space. So here I have the probability of anything in the sample space given that we have B. Now, if you think about it, given that we have B, that's an event in the sample space. All right, so automatically, just from setup, we're in the sample space. So when I come to here, the probability S intersect B, well, B is a subset of S, therefore this is just B. And I see that I have the same thing on top of itself in a fraction, therefore the entire probability is 1. Now, things get a little bit trickier on this one. So remember, we have that whole mutually exclusive events aspect when we're talking about the axioms of probability. If I take the union of mutually exclusive events, the probability of the total is the addition sum of the individual probabilities. Okay, so the probability of any of the mutually exclusive events A, given that we know that B has occurred, well, what I'm going to do is I'm just going to apply the formula. So here I'm using the formula where I had A previously, I put union of all of the A's with a subscript. And I'm just running through the formula. Okay, so now I have this inside a probability. All right, so I have an intersection. I have a union, and I have a union of multiple sets and an intersection. There's a distributive property on unions and intersections, so I can distribute the intersection with B across all these. Okay. Now, something to realize is that because all of the individual A's are mutually exclusive, it works out automatically that all of these intersections have to be mutually exclusive. I'm taking a union over a bunch of mutually exclusive events. Therefore, I can use the summation formula. I can pull that union out of the probability and convert it to a sum. Boom, we've got this. All right, so now I have a sum of probabilities in the top of my fraction, and I have the same number in the bottom of my fraction. I have one number in the bottom of my fraction. Well, I know from my college algebra, I can distribute this across that summation. And so here I go ahead and do this. So here I can see up top, I have the entire summation, and I'm dividing the whole thing by this probability of B. What we're going to do, we go through and we distribute that probability of B across all of the individual terms in the sum, and we get this part of the equation. All right, now if I look at this, I see that this is the conditional probability of A sub I given B. Boom, we've got this. And so now this satisfies the third axiom for us. All right, so now something that is important for us to think about is the informative value of a test. So think about a diagnostic test. I go to the doctor, and the doctor and I want to know, do I have a certain disease? Yes or no. And so I'm going to take a test. The lab tech is going to run some stuff on my blood or some other fluid from my body. And then they're going to check, and it's either going to be positive or negative. Now, it's possible that it's positive and that is the correct value, or there could be a mistake, or there could be an error. Maybe there was a pollutant going on. Maybe the lab tech handled things incorrectly. Maybe there was a machine processing error when the test itself was built. A lot of possible mistakes can come into this. And it could be that positive value is actually incorrect. So I have something called a false positive. Now, what about negative? Well, it could be that the negative value that I got from the test is correct, but it's also possible that there could be a mistake there. So maybe in the process of collecting a sample, not enough was taken, but the lab tech still proceeded with processing the test. And so there wasn't enough sample to get it to be detected correctly. And so then I have a false negative. All right, so when I have a positive test and I have the disease, that is a correct positive. If I have a positive test and I don't have the disease, that would be a false positive. If the test is negative and I have the disease, that is a false negative. If the test is negative and I don't have the disease, that is a correct negative. Okay, so overall, I want to know, what is the accuracy of this test overall? Well, that's going to be the number of correct results. So if we were to go through and start evaluating this test, let's say we go out, we find 1 million subjects, we run the test, and we know if they have the disease, yes or no, and then we compare the test to our known value. All right, so we take all the correct values, and we divide by all the values total, and that gives us our accuracy. Now, something about this number, if I'm talking about a very rare disease, I can get very skewed results. If I have a disease that's very, very rare, I could have a disease that always says negative, and that's highly accurate because of how rare the disease actually is. So what we want to do, we want to make an adjustment for the situation that we're interested in. Sensitivity is going to be all the correct positives divided by correct positives plus false negatives. All right, so here I'm taking all of the correct positives divided by the total number of times that we have the disease. All right, so here the text has the disease and detects it divided by all the times that the disease is present in the subject. That is the sensitivity. The specificity is going to be the number of correct negatives divided by correct negatives plus false positive. And so here, this is going to be the number of times that we have no disease. So number of times that there's no disease and the test is correct divided by the number of times that there's no disease, period. And this is our 3 major ways of measuring the accuracy of a diagnostic test. All right, so now let's keep going. Let's think about independence. So first thing I want to say is, in general, probabilities are very sensitive to conditional information. This is very important. And this conditional information can be very intuitive. The exception to this is when events are independent of each other. Okay, so probabilities are very sensitive to conditional information. All right, so if they're not sensitive to conditional information, that's going to be something that we call like independence, that the other information doesn't play a part, isn't important to it, doesn't have an influence. All right, so independence is actually a very rare event for us to be worried about, but it's a very powerful result. It mathematically gives us a lot of things to work with, so it's a big deal. Anytime you look at a statistics textbook, independence is a big deal, and it's a very rare situation for most cases. So here, we're going to say that two events are independent if the probability of the intersection is equal to the probability of them being multiplied by each other. Okay, so when A and B are independent, then the conditional probabilities just become the regular values. The probability of A given B is equal to probability of A, and the probability of B given A is just the probability of B. And that comes from using this for the intersection in the formula. Now, the law of total probability, this enables us to compute probabilities over smaller components. So the idea here is that I don't want, if I've got something that's kind of like just too unwieldy, I can't get my arms around the whole thing, what I can do, I can break it down to smaller components, work with the smaller components, and figure out what it is I actually want. All right, so for any event B, the sample space can be broken up into the event B and the complement of B. Okay, so that means that any event A, another event, I can break up A into A and B, or A and the complement of B. And so because these are mutually exclusive, I can convert the probability of A into the probability of A and B plus the probability of A and B complement. And next, I can use conditional probabilities to do a conversion on the intersections to give us conditional probabilities. All right, so the punchline here, there's actually two. The first one is this line. Probability of A is equal to the sum of the intersections. And then the probability of A is equal to the sum of the conditions times the probability of the partitioning event here. All right, so what this does for me, if I need the probability of A, but I have individual components, not A itself, I can use these to get at what I actually want. Now, this is when I just have one event partitioning the sample space into B or not B. That is the question. If I want to do it over a partition of the data set, so remember, a partition are mutually exclusive and exhaustive over the entire sample space, then what we do, we go through something very similar. I know that S is equal to the union of all the B's. Then when I look at A intersect S, that's A intersect the union of the partition. I distribute the intersection across all the B's using that distributive property. So I get this. Now I know the probability of A is equal to the probability of this intersection union business. Well, I know that these events inside here, that the intersections are mutually exclusive of each other. So I know that these unions can be converted into addition, like this. And now once I have the intersections, I can convert the intersections into conditional probability statements, and I get this. All right, so why is this important? This gives us a way that if I'm interested in A, but I don't know A directly, I know its relationship with B, I can still compute the values. Now, Bayes' theorem, what Bayes' theorem does is it enables us to reverse conditional probabilities. All right, so if I'm in a situation where I know A given B, but I don't want A given B, I need B given A, switch it. I know A given B, but I want B given A, I use Bayes' theorem. Anytime it's like, man, I wish I had it the other way around, think Bayes' theorem. All right, so the punchline of this is that the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A given B plus the probability of A given B complement. And if I want to do this over a partition instead of an individual event, then the probability of B sub j given A is equal to the probability of B sub j times the probability of A given B sub j divided by the summation. The one that's most important for us is going to be this one. This part, that's probably the one that we're going to be working with the most. Now, for our assignment for this one, what we want to do, we want to go out and we want to find what is the accuracy, sensitivity, and specificity of a medical test. So for this example, when I'm filming the video, I might change this test when there's another disease that breaks out. We're going to look up the information about the COVID-19 test. We want to compute the accuracy of the test, the sensitivity, and the specificity. Then we want to fill in the table for when there would be 100 patients. So given the accuracy, the sensitivity, specificity, and 100 patients, we want to fit that correct positive, correct negative, false positive, false negative table. All right, that's all I've got for you. Take care and goodbye.